Anyway, I was not the reservoir. So the previous class was too long. And now that. Welcome. Great. Did you see the basket? No. Okay, great. rust. So, good afternoon. Sorry for the late start. It was not my mistake right now. I was here thanks to the Hungarian Railways. I arrived in time. Just the previous lecture kept longer the lecture. I have good news. For example, I got access to the Neptune. Also, I find access to the Moodle, so I can upload the stuff, material to Moodle and not to GitHub. That's one thing. The other thing, now I know the appropriate sign and name of the lecture. It's also good. I still don't have, internet connection, but, you know, well, time will help. Well, I'm still in trouble, and actually you are in trouble. I checked where we are. One of you sent the second, the third, and the fourth lecture, and I know what you had done. It was great, just it does not lead anywhere along. So I sent a message to Mr. Szilárd Zsóka, and I haven't got any answer. So it seems to be in Hungarian universities, at least the four where I studied and taught and worked, answering emails is a luxury or something like that. It's almost a perversion, perhaps. I don't know. So the only information source is you, the Moodle, and the Neptune right now. What I know, you had no practice at all, just only me, and I made a mistake. I sent you the image and we will discuss it. And the problem is that I got two versions of the syllabus, and one says you have to write two tests. The other says you write one test.
Last semester we understand the end of the semester and then the exam.
Okay, that's the normal.
And the homeworks.
Sorry?
What he said plus the homeworks.
Yeah, but that's the
Okay, so there was only one test. And the homework. But you still cannot do the homework because, for example, you don't have homework and you have no experience what to do. It doesn't matter. I will tell you what is the lecture. I finish it. Then we have a break and then we continue with practice. The problem is that, so one test. Then means I have to give you homework. How many times did you have homework? 3 times, 5 times?
6 in total.
6?
And yes, and we need to do at least 3 of them.
Okay, that's great. More work to me, doesn't matter. Okay. Okay, I told you. Now, the next problem is where we are. So what I know, and we discussed, is this motionless of charged particles in electromagnetic fields that was given last semester during the spring. Elements of quantum mechanics, Heisenberg classical principle. I saw this in your notes with many Hermian matrices and operators and everything. Okay, the thermal radiation that was given to you last time. I improved the test and the images in the meantime, so everything is in English in the final form. Now I will talk about special relativity theory and the other things. The problem is the following. This classical theory of atomic structure, Rutherford, Bohr model, quantum numbers, Colin exclusion principle, do these terms say anything to you? During this, we are very far. So could you, can anyone show me the notes from the very first class? Thank you. So this, okay. So this was just but this is yes. Okay.
I think this one is
Okay. Here. Oh, that's bad. That's really bad. It means you don't know anything about the rudder for the atomic model, or war model, or something like this. Never heard about it. Do you know what is a quantum number? Yes. Have you ever heard? This lecture. Okay. As we did. Great. Okay, thank you very much. Thank you. That's enough. It means you will have a brief lecture because that one, this italic, haven't been told to you. No problem. Next time I will tell you, and I will also tell you the last slides of this chapter because you will not understand it perfectly. But you know what is this Heisenberg uncertainty principle, and you have seen Schrödinger equation. Don't worry that you will need only at the end. I will have very interesting topics today, and then we will switch to practice. So, special relativity theory. Have you seen the interstellar? This is an assignment. You should see it. Actually, the topic is a bit different. There are two relativity theories. One is the special relativity theory. There are inertial reference frames. When the first law of Newton is true. There are others when, for example, there is one reference frame and there is another which is accelerating. That's the general relativity theory. The first one, when the two reference frame is has the same velocity, or one has a velocity which is unique and the direction does not change, then that's a special relativity theory. Why special? Because it is limited to these reference frames, inertial systems. This is a big difference. The first, historically, the first difference is Lorentz, Minkowski, Einstein, and others did this special relativity theory. At the very end, I will explain you some elements and why is it important. And then I will tell you something which related to quantum mechanics. It goes to antimatters and other science fiction terms, which is not science fiction actually. The general relativity theory is valid for any reference frame, and that's the creation of Albert Einstein and his Serbian wife, who was very good in mathematics, but she had no degree. Later they divorced, and also some mathematicians. That is the theory of gravitation. The theory of gravitation, you know the Newton law, you know the formula, but the Newton law doesn't explain what is gravitation. The gravitation is nothing more, just a twist in the space-time, in space and time together, and it is caused by the mass of the test. Your mass or our star, the sun's mass, the earth mass. That's the explanation. We will not talk about this. Last Friday, I was an opponent of PhD defense. This is the topic of interstellar, black holes, gravitation time direction. If you check the Interstellar, just visit it. It's a good movie. It's a really high quality movie. And also Thorne, Professor Thorne, who just got a Nobel Prize, was one of the experts. So it was really good how the event horizon looks like. It was described, the time direction, and some, how can I say, poetic content is given. I will explain you and I will show you some stuff. I hope I have some internet, but you forgot to tell me, and I also forgot to start this OBS studio. Yes, because I record everything, so where is it? It's here. Okay, this is just 1, 2, 3, 4. No, where is it? Here. That's. I will start. Yes, I start. Nothing videos is here. Okay, it works. In the old days, when I taught at Milton, my mic very often disappeared, and that was a bit awkward. Good afternoon. Okay, so I just started the record, but in the other record you can see what happened. Mostly nothing. I just explained the difference between the special and general relativity theory. Okay, so the gravitational theory, which is very interesting, is this time dilatation. Now, if we have a very sensitive, very accurate clock, atomic clock, and we put another at the top of Galilee, for example, then our clock will go slower than that one. The navigation, the agriculture, the everything nowadays is based on GPS. It's a global positioning system. Segíthetek valamit? Can I help you? Hello? Thank you. So, GPS, global positioning system. There are spacecrafts around 500 or 600 kilometers tall, and they have a nuclear clock, atomic clock. Our clock is slower than that clock. The difference is very small, but because of the high speed of light, and they use the radio waves to determine the position, that cause very big difference. Very big means meters, if I remember well my calculation. And 25 years ago, this GPS system were very sensitive, so it was possible not only just bomb or fire a rocket to a window, but also one seat in the room. So the general theory is important. You will not learn it, it's very difficult. Okay, time dilatation. There is a very nice thing. It's called gravitational lenses. Gravitational lenses, I should have put something here. Okay, then I will show you. So we are out. We are here, and we can see a star. And if the sun is here, then these stars looks wider because the light, the photons, will not propagate straight, but it's a curve. And this is the prediction of the general relativity theory. If you look there, and you have a galaxy far, far away, and there is a further galaxy, then the gravitation of the first galaxy behaves like a lens. You can see duplication or multiplication of the galaxies, and also very, very, very twisted forms. There are many beautiful images of this. Just I didn't add to the slides. Yes, and I would like to show you something else, which is related. This image is not from the interstellar. This is the GPU laboratory. Okay, yes, you see. I don't know how I can stop this. So this is the GPU laboratory, computational laboratory of my research institute. Do you know what is GPU? Graphical Processing Unit, not CPU. Oh, this is it. Oh, so I have this, and where is the print screen? In this. Oh, there. See. Again. Oh, here. No. Okay, here. Great. Not perfect, but better than nothing. Oh, I know what happened here. Will you please be quiet? I am talking. I'm the lecturer. Hello. Thank you. Silence. Here it is. Next one. Here. Okay, so I saved it, and this is something special for you. Here, okay. So what is it? This is a black hole, and it has an event horizon, and the matter falling in the black hole forms an accretion disk. However, the distortion of the space is so strong that you can see the foreground, of the disk, and you can see beyond the black hole, and this is the other part of the disk. So this is not here, this is a disk, just the space-time has been twisted, and you can see the other side of the disk, which is normally not visible. Yes?
So probably that's if it's a disk with a central bottom left part of the disk is that if the adapter part is the disk just then.
Yes. No. The disk is the shape.
Yeah.
The shape of the disk is disk. It's okay. It's almost planar. Just you can see what is behind the black hole, because it distorts the space so badly that the light go around the black hole and view what is behind the black hole.
So the third part in the lecture is like a disk.
Yes. The shape of this. You have nothing here. There's the black hole, and there is an accretion disk, and it's rotating. So it's a disk. This is the shape, but because normally you would say this, you would see this like this. But okay, it's not good in. Normally you would say you would see something like this. But because I turn this, the light changes. The light, so it's like a lens. Then you see this part and this part, and this is the observer. So you see this that upper part because of the distortion of the space. But this is just an interesting thing, and you will not write tests from it. But I try to take your attention for other things. Okay, so watch Interstellar, it's great. Let's start with this special relativity theory. Actually, you have learned something about it. You have learned aerodynamics, didn't you? Mass regulations. Last year you should have learned it. No?
The end of the mass calculations. I don't know, we didn't have it in our big test.
You haven't had aerodynamics? Not yet. That's a problem. Okay, I thought you had. Oh, sorry, I crashed with here. Okay, let's start far from the special relativity theory, and then we will go to antimatter and annihilation. I hope you like exposures and some stuff like this one. So let's start with the Italian guy, Galilei. He was a good astronomer and astrophysicist, and he had some observations, and to honor him, we called this stuff this variant principle relativity. You know reference system, you know inertial reference frame, and you also know the moving uniform straight line That's the term. You know this. Egyenes magnetes mozgás in Hungarian. So it's a straight and there is no acceleration. If you are in a train, everything is covered by, all windows are covered by curtains, then in theory you cannot distinguish whether the train is moving or not. Well, the Hungarians are bilingual. Our first language is Hungarian, the second is sarcasm. That's why I put some train from the Hungarian airways, because the railways, because in our trains you are jumping, so you know you are going. I assure you, if you go in France, in DGB, or intercity access in Germany, or you use a magnet in China, I haven't been in Japan, then you can put a glass of beer or Coke and it stays there for hours. So that's really a straight movement and really without acceleration. So if you are here and everything is covered, then you cannot distinguish whether you are moving or not. That's a principle. That's the Galilei principle. Well, yes. Okay, what happened when you have two reference frames? One reference frame is K, the other is moving. The K is at rest, the other is moving. The velocity of moving is this V0, and you have this. I don't have pointer. Okay. This is the origo. This is the coordinate system. This is the other coordinate system. Everything is with this comma. This is the key comma system. We have a point here, P. It has a position. This R vector. In another system, we have this R comma position, and we know very well that we have this origo and we have this origo, and the difference is given by this R0 vector. If you check this and go back, because how can I go back? Okay, yes. You can see that this R, comma, and R0 gives this R, the original R. It's the same coordinate system. Okay, let's do a derivation by time. We got the velocities, which is good, we have the velocity. We do this derivation again, we got the acceleration, and this acceleration, this A0 is 0, because this is not an accelerating system. But we can do the acceleration. If we do the multiplication with the mass m, then we got the forces. So it means that if you are in a other reference frame which is moving uniform in a straight line, then the forces are the same. If you take a bus and it turns, of course it's not true, but we excluded these systems. We are in special relativity right now, not special relativity, just special frames. So, the reference frame that are at rest or moving uniformly linearly relative to each other are completely equivalent with respect to mechanical phenomena. If one of them is an inertial frame, then all of them are. The consequence is that if there is one inertial frame, then many inertial frames exist. And from Newton's first law, we know that there are at least one. So there are many reference frames. Let's go through what I had done. It is written here. The positions of these systems can be calculated in this way, the velocity in this way, the acceleration in this way, and this is the time. This is very important, the time. The time flows with the same ellipses, flows the same velocity in all reference frames. This is the classic Newton system. This is the these are the classical mathematics right now. Questions? What about the laws? Mechanical laws, electrodynamical laws, and other things. Will these laws be valid in this Gaussian transformation and Gaussian systems? The answer is that yes, mostly. With restrictions. There is one which is very rare. It's the electrodynamics. The electrodynamics, the Maxwell equations and Maxwell-Taylor's electrodynamics, was made at the end of the 19th century, and that's Lorentz invariant and not Gaussian invariant. I mean, the Gaussian transformation is not good for those equations. Actually, it's unexpected. But can you tell me what is the difference between a charge and the current?
The charge over time.
Sorry?
The charge over time. It's like.
Yeah, it's something like this, but with one word, if charge is moving, then it's current.
Yeah, and the flow of charges.
So it means that the currents and charges and everything are dependent on the chosen reference frame. So there will be a problem with the Maxwellian electrodynamics. But that's a nice problem, actually. So that's a very good theory. Okay, now I have to wait. So the class started at okay. Let's. I have time until okay. I still have 45 minutes. Great. So we have to do a couple of experiments. First, we introduce this light clock. It's a very interesting thing. You have a light source here. It emits only a few photons. There is a mirror, and it goes back. I don't know why it's a clock, but its name. Okay, let's see first. We have this experiment. We have this light clock. We have t1 time, v velocity, and it goes. Then we can calculate the distance of the tube, and also we can calculate how much time, what distance, what is the distance, what way, what road did this light did. The c is the speed of light everywhere. If you check this and yes, you have this L, you have this time, you have this equation, and you can get this T1 time. Let's do it again with longer T2 time, and then we got this expression. How can we calculate the total, the sum of these times? Normally we add them together. But if you do this experiment and do this, you have this formula, you got this. These are fractions, so you can do the calculation at home if you want. Let's check another experiment. Now the propagation is perpendicular to the tube, and the light goes in this way, the tube goes in this way. This is the length. Using the Pythagoras theorem, we can calculate this as the sum of this side and this side of this triangle, and we have this time. So we have the total time, but this total time is not that time that we expect, what we calculate. So we expect that the total time is T1 is T2. But with this experiment, we have different times. Something is not good. Something is bad. Okay. Train again, or it's better if you have a photonic spacecraft. It's the rocket goes by photons. But you can also go by trains. Okay, the train is going with V, and there is a person running forward with V. It's written C. I will switch to C, but I just say right now V. Okay, very simple. His velocity is the velocity of the train, and his velocity comparing in difference frame of the train. That's normal, that's okay. What happened if you emit light here? Its speed is c. Whether the velocity is the velocity of the train and the velocity of the light, this was expected. And why? So that's normal assumption. Okay, then you can add together. No, you cannot. And to find this, they did this experiment. It's called Michelson-Morley experiment. Actually, there is something that is not written. When they had the electromagnetic waves, the electromagnetic waves are very simple. You have changing electric fields that makes magnetic fields. The magnetic field change, and it gives you changing electric fields, and it propagates. But they could not understand this, and they looked for a material which is resonating. This hypothetical material was the ether, which does not exist. But there is this experiment with seems to be a very bad resolution. What happened here? This is an interferometry experiment. There are two beams of light, and the one is go through a semi-transparent mirror and has a longer way. And the result of this experiment is something interferometry rings. And we are here on the Earth. It was well known 1.5 centuries that the Earth goes around the Sun. The velocity is approximately 30 kilometers per second. So, we have the light, we have one orientation of this experiment, and if we are parallel to the Earth moving vector, this 30 kilometers per second, then the speed of the light increases, and we got some interferometry sample. Then we turn around, then it is anti-parallel to the Earth, then the speed of the light will be less, so then we get other interferometry sample. We also can do perpendicular to the movement of the Earth, then we don't see so much. My head of class in the secondary school said it is a feature of someone if he or she does not like poppy seed pasta. Az is tulajdonsága valakinek, aki nem szereti a mákos tésztát. This is a negative experiment. They could not see the difference of the light, because there isn't. In vacuum, the speed of the light is always the same. This is an observation. This is a feature of us. This comes from Maxwell equation, for example, but which is unexpected, that the light will not change. So I cannot do that, okay, I'm going with a train, and then add the velocity of the train and the light, and not something else. It's not possible at all. The speed of light in vacuum is the same. And this is the result of this Michelson-Morley experiment. And also a result there is no later, but we don't mention this later stuff. It's just historical. It's not important for you. This fact says something. It means the Gaussian transformation is not always good. It's not good for light. So we need something else. This something else is the Lorentz transformation. And this is first was found valid for electromagnetic radiation and this electromagnetic theory. Again, we have two reference frames. One standing or resting, actually. Resting is the better, correct, rest is a better term. This scale. We have clock, we have Mr. Observer, move, megfigyelő, and we have another reference frame, and that reference frame is moving with uniform linear moving reference frame. That is. Also you have a clock, also you have a scale. We are happy. If you, and I will not explain because we cannot stay here until midnight. If you do this transformation, that transformation is different than the other. If you are in the first system and you want to transform x, y, z, and also the time from one to the other, you have to use these forms. Time changes and depends on the position. And also the coordinates are different. Of course, not all of them we choose one. There is an inverse when for the second frame you transform for the first one. Then the forms are different. But there is this square root form. The v is the speed and the c is the speed of light. This is always there. If the v is bigger, larger than c, then you have a negative number under square. It's a complex number, imaginary number. We cannot accept this. So it means that from this formula that you cannot exceed the speed of light, and I assure you, you cannot reach it if you have a mass. If we are here at the bottom of everything, and our speed is quite low, then this v per c square and also the square root will negligate it, and t comma will be t, x comma will be x. So it's you will get the Gaussian transformation. But if you are close to the speed of light, then everything changes. Then you have to use this formula, and actually, yes, there is some stuff, this 1/6, but well, it's definitely. Okay, let's switch to more interesting thing. If you see a spacecraft with large speed, then that will be compressed in the direction of the moving, if the speed is close to the light speed, the speed of light. Check this formula. This L is the length of the spacecraft or anything, and the other in this the L comma is this in this moving system. That's okay. There is something else. Perhaps you have heard about the twin paradox. There are two twins. One stays with Earth, the other visits, I don't know, Alpha Centauri, Tau Ceti, whatever, and he travels close to the speed of light. Then they return, and the guy who traveled remained young, the other became older, because the time slows down if you approach the speed of light. This is a twin paradox. At the end of the interstellar, there is a more brutal screen. There is a time dilation if you are in strong gravitational fields, and the main hero, the protagonist, travels and spends time in a gravitational field of black hole, and when he returns, meets his daughter, and when he returned, he was 35 years old, the daughter was 9 years old. When he returned, he remained 35 years old, but his daughter became 90 years old. It's very good in the movie when the daughter is an old woman, old lady. She's dying, and the young father approaches. That's more brutal than this twin paradox. But that's general relativity theory and time dilation by gravitational fields. This is time dilation by high speed. Okay. Some principle from Einstein. You have heard the name of Lorentz, now Einstein. Principle of equivalence. All inertial reference frames are equivalent for describing any physical phenomenon. In other words, reference frames are at rest or move uniformly in a straight line, relative to each other, are equivalent for all physical laws. We are not physicists. It means that this first sentence, this principle, you apply the Lorentz transformation, this coordinate and time transformation for laws and everything, then you got the same somehow. So you sum the same laws. This is called invariance. Doesn't matter. It's not good. The principle of constancy of the speed of light. The speed of light is an universal constant, independent of the motion of the source, the observer, or the reference frame. This value is approximately 3 times 10 over 8 meters per second. The speed of light in vacuum is the ultimate speed limit. It cannot be reached or exceeded by any object. Yes? Okay, so this is from the Michelson-Morley experiment. That's an experiment. The speed of light is constant. Its value came from the Maxwell theory, the theory of electrodynamic waves, and which is very rare that you cannot reach it. Everything that has mass cannot reach it. I will show a formula that proves this. The photons, the light particles, electromagnetic particles, they have no mass. So they can travel by the speed of light. There are crazy theories that there are particles which go much faster than light and they can reach from above the light speed. That's crazy theory. In Star Wars and also Star Trek, there's a warp when you open a window and in this window the law of the physics changes and the speed of light becomes much higher and then you can travel 10 times c. We don't know this, but at least they consider the law of physics. So what we know right now, if we want to go to Proxima Centauri, that's approximately 4 light years old, so the light needs 4.3 years to go there, then we have to travel more than 4 years, 5 or something like this, because we cannot reach the speed of light. Actually reaching this speed is also a lot of energy. You will see very soon. My comment, it's not part, but interesting. You cannot exceed the speed of light in vacuum. If you have special conditions, then you can exceed the speed of light in a transparent material. For example, water. Do you know what is Cherenkov radiation? Have you ever heard about Cherenkov radiation? You who have seen the movie, HBO movie of Chernobyl? Okay. Doesn't matter. Actually, I will not explain, but the radioactive sources, radioactive particles, has very high velocity. That high velocity is lower than the speed of light in vacuum, but it's higher than the speed of light, for example, in water. The Technical University of Budapest has a nuclear reactor on the shore of the Danube, yes, in the middle of the city, between, what is the name, this Franz Josef Bridge and Margit Bridge. Its power is something 100 kilowatt, And the reactor is under a 5-meter pool. It's actually not really a pool, but it's something, it's not so bad. I made experiments with it, measurements as a student, and if it's dark, then you can look at and you can see a beautiful beautiful blue lights between blue and green. These are the particles, the radioactive particles. They go in the water faster than the local speed of light in the material. And then there is a deduction. That was the 20th topic of my modern physics board exam. Well, and nobody was given for it. There are radiation, and this type of radiation is very similar like supersonic stuff. When you have a fast airplane and it goes faster than the sound speed. Doesn't matter, it's very nice. So you always have to say the speed of light in vacuum cannot be exceeded or reached if you have mass. But in vacuum, that's the important thing. If you check this and compare the results of this Michelson-Morley experiment, then it says that time goes different speed. So there are some other things. This could be deducted, but it was told to be not deducted. First, there are two masses. One is the rest mass. We will talk about this. And there is the mass which depends on the coordinate system. If you go so fast that you approach the speed of light, then your mass will increase. If you check this, you have a rocket. You want to go travel somewhere, and you accelerate. Then your mass will increase, and you will never reach the speed of light, because the force, the energy that should have accelerated you, increases your mass. Actually, the reason is that the mass and the energy are the same. Actually, just it is it was not known previously. You can calculate the momentum and the total energy. This is Einstein's very famous formula. E is equal to m times c square. This is the equivalence of mass and energy. M is mass, c is the speed of light. And there is a formula. M is the resting mass, and if you move, it changes. Okay. Yes. If you are lucky, then you can get energy from atoms. I will show you within a few minutes what is annihilation. Then 100% of the mass became energy. But if you have a nuclear power plant or a nuclear bomb or thermonuclear bomb, then a very small part of their energy mass become energy. It is possible, or if you don't have nuke, if you just burn, for example, carbon and oxygen, then the mass of the products will be less than the original total mass of the components. The difference is very small because the chemical energy is small relatively nuclear energy and annihilation, but it's possible to measure it. The sun, you have in our sun, there is thermonuclear fusion, and its mass decreases all the time. Just it's so big that you cannot see the difference. Okay, if you calculate kinetic energy, then you have energy and you also have to consider the speed of light and also the resting mass. And this is that I tried to explain once. There is the fundamental equation of dynamics, the second Newton law. That's dm times v mass times v. Its time derivative is the force. But now here we are in special relativity, in Newton relativity, in Newton theory, classical mechanics. The mass does not change. Here the mass can change. So it means that you have to consider this. This is what I told you. You accelerated your rocket. You are chasing the light. You want to go faster and faster. And after a while, you will recognize that your mass is changed. The acceleration is slower, less and less, and once it becomes zero, infinitesimal, because you cannot reach the speed of light. If you don't understand this, then the problem is not in your machine, in your computer. This is not understandable by logic and mathematics. But this is not what you can see. There are four regions of our world. One, the small, then the macroscopic. Also we have speed, which is close to the, which is much lower than speed, and we have speed related to c. Okay, what we can see? We have macroscopic world. This is, we are slow, macro world. This is the Newton mechanics. This is our world. There are small. This is quantum mechanics. At the very end of this class, I will tell you something which is small and close. Its speed is close to the speed of light. We know something about this. However, we don't know nothing, or almost nothing, related to places which are macroscopic and go with speed of light. That's the black holes. There is a singularity beyond the event horizon, and we don't know what is inside. In the interstellar, they find the tesseract. That's fantasy. We don't know what is inside. We know close to the event horizon what we have. Also, we don't know how the universe not created, appeared. We don't know the Big Bang. We don't know what was there. So this is a big question. There are theories, crazy theories, normal theories, nothing works right now. And, okay. This E equal m times c square means that the energy and the mass are the same feature, the same property of the matter. Energy and mass are the same. Mass and energy are inseparable manifestations of matter. This is from Einstein. And this is a very important stuff. Okay. Now I have 20 minutes. It's enough for a Cooper test. And this is not part of the topic, but I think it's interesting. So I explain you. This is this relativistic quantum mechanics. You learned the Schrödinger equation. The Newton equation is good here. The Schrödinger equation good here. And here, when you have small particles and high speed, the Dirac equation is good. It was made in the 20s of the last century. I do not explain everything which is there. There is this wave function, and this wave function, you have a lot of things. This is invariant to the Lorentz transformation, and also gives back the features of particles. But there are more, and that's why I explain you and show you. Okay. I told you there are special and general relativity. There are, yes, this is good for special relativity. There is no quantum mechanics in general relativity, that would be this one. This is special relativity, and gives some very interesting things. The fundamental features of particles, for example the electron, are given. The charge, the mass, no, not the mass, just the charge. It describes with the wave function the electron. However, it has two solutions. One negative, minus, and one positive. So, there is electron with minus charge, and also there is an electron with positive charge. Its name is positron. Not from the Dirac equation, but you can do the same with protons. If you have protons and electrons, then you can put them together. The charge of proton is positive, but there could be an antiproton, its charge is negative. So you can take a negative antiproton, a positive electron, a positron, and you have antimatter, antihydrogen. That's very good. You have this beam, you destroy everything. Is there anyone from Poland? No? Do you know Stanislav Lem? He's a Polish and very good sci-fi writer, and he liked antimatter bombard. You, instead of nuke or thermonuclear bombard or laser or anything, you put antimatter. Because, that's the end, but I show you now. If an electron and positron meets, then they destroy each other. All of their mass become energy, and two gamma photons will be radiates, which is not in direct theory. It is possible that from gamma photons you can make electrons and positrons. So if you have antimatter, it's quite expensive, You can do it in accelerators, in CERN and everywhere, but only a small part. You can destroy full currents, or boil full seas or oceans if you want. It's better than that stuff. Just it's very, very expensive because for all mass you need a lot of energy. If you calculate how much energy is necessary, then we don't have so much energy. But it's very rare that the universe seems to is from matter and not antimatter. Because if there would be, for example, a planet or a star system in the Milky Way from antimatter, it would be touched with normal matter and we would see radiation. So there is a symmetry between matter and antimatter. But it could be full galaxies or stars from antimatter. We don't know, but it seems to be everything is from matter right now. But antimatter exists. This is, I think, interesting, and it will move to explain you. Okay. Then, next class, I will explain you the quantum numbers and the spin. The spin is not rotation, it's a type of symmetry, and it's very important to explain the features of the chemical elements. But from quantum mechanics, you can't explain it. This direct equation gives the spin and its quantities. Yes. Okay, everything is Lorentz invariant, and if you go to low velocities from here to low velocities, then you got quantum mechanics Schrödinger equations. Yes, I told you the spin. That's a momentum, antiparticles. Bang. That's the annihilation. Yes. Okay. There are more. This is an old theory. When I was before specialization, I had to learn relativistic quantum electrodynamics and also some elements on quantum color dynamics. This gives the mass of proton and also the parts of the proton, quarks. And this is the modern physics, and the last piece of this modern physics was discovering a particle called Higgs boson. And he got Nobel Prize, and the power plants and funds got a lot of money because the accelerators need a lot of energy to prove this. Okay, so the direct equation gives you this wave particle duality, Lorentz invariance, and some the antimatter and the spin. And that's a good thing. My colleagues, most of my colleagues at Wigner, deal with this. They are particle physicists. It's a very special type of physicist. Thank you very much. Thank you. And now I stop everything. We have a break, 10 minutes, and I will continue with the calculation because you need this. Okay? Thank you very much. We stop recording everywhere. Oh.